How can two steel machines weighing a combined 800,000 to 900,000 pounds pull a freight train that can exceed 10,000 tons across hundreds of miles without tearing themselves apart? And what invisible forces make that possible? Stay with us as we unravel the hidden physics and engineering behind modern rail, and subscribe for more deep dives into the secrets powering our world. Steel wheels on steel rails seem like a recipe for disaster. Thousands of tons balance on contact patches no bigger than a coin, all relying on a pair of locomotives to keep everything moving. The secret is not brute force or overwhelming horsepower. It is physics, specifically the astonishingly low rolling resistance that steel offers once the train is in motion. A fully loaded freight train stretching over a mile and tipping the scales at 20 million pounds has a rolling resistance coefficient called CRR of just 0.0017 on well-maintained track. That means the force needed to keep the entire train moving at speed is only around 34,000 pounds. For perspective, that is less than the weight of a single modern fire truck. It is an order of magnitude lower than what rubber tires face on asphalt, where deformation and friction eat up energy at every turn. But this advantage appears only once the wheels are rolling. At rest, every axle and every wheel must overcome static friction. The initial force required to break that grip, summed across hundreds of axles, can dwarf the rolling resistance by a factor of 10 or more. It is why starting a train is so much harder than keeping it moving. The invisible interface, the Hertzian contact patch, spreads each axle's load across a steel-on-steel surface measured in millimeters, concentrating force and making slippage a constant threat. The numbers are clear. While a moving train needs just 34,000 pounds of pull to glide along, the real challenge is getting all that mass to budge in the first place. That is where the next layer of physics, adhesion, and tractive effort takes center stage. For those who want to see how two locomotives wrestle with the limits of friction and force, stay with us and subscribe. The deeper we go, the more the hidden logic of railroading reveals itself. An SD42 locomotive presses 368,000 pounds onto the rails, with each axle carrying about 61,000 pounds of normal force. The contact patch, smaller than a coin, defines the upper limit of usable tractive effort. With a coefficient of adhesion between 0.3 and 0.35 on clean, dry rail, only about a third of that weight can be turned into pulling force before the wheels slip. That sets the ceiling. A single SD42 can produce up to 115,000 pounds of starting tractive effort, or 230,000 pounds when two units work in tandem, provided every pound stays just below the slip threshold. The diesel's 3,000 horsepower does not go straight to the rails. It is converted from engine to alternator, then split among 6 D77 DC traction motors. Each motor delivers roughly 10,000 pound-feet of torque at low speeds, holding a flat torque plateau up to 300 revolutions per minute. As one traction systems engineer explains, we design for a torque curve that is flat as a table at low speed. That way, the motors push right up to the adhesion ceiling without burning out or slipping. Wheel slip control systems, first analog and then digital, constantly monitor each axle, keeping wheel speed just below the slip point, usually a 2% differential. On dry rail, adhesion can be held at 27%, but it drops to 16% or less on wet track. Every start is a careful balance, enough force to move the train, but never enough to lose grip. Every freight car in a North American train is joined by a coupler. More than just a steel hook, it is a carefully engineered spring damper system known as draft gear. Hidden inside each coupler is a set of powerful steel springs and friction pads designed to absorb shock and meter out force. The numbers are precise. A modern coupler's draft gear is rated for a stiffness of about 12,000 pounds force per inch. That means for every inch the spring compresses, it resists with 12,000 pounds of force. The total slack, the free movement before everything locks up, averages about 3 inches per coupler. Elasticity is not a design afterthought. It is the secret to how two locomotives can move a train that on paper seems immovable. When the engineer eases the throttle, the head-end coupler compresses first, soaking up the initial surge of force. Only when the spring inside reaches its limit, typically around 30,000 pounds of compressive force, does the next car begin to move. The process repeats car by car as the force travels down the line. Instead of demanding the locomotives overcome the inertia of 10,000 tons in a single brutal tug, the draft gear smooths the process into a controlled sequence. Each coupler's slack acts like a buffer, letting the train stretch out and absorb the shock. This is why when a mile-long train starts rolling, you can watch the wave of motion ripple down its length, each car engaging only after the one ahead has taken up its slack. The mechanical design limits the peak force seen by any single connection, sparing both the couplers and the rails from catastrophic overload. With the coupler's anatomy laid bare, the next step is to watch how this force travels, a slow-motion chain reaction that lets two locomotives do what brute strength alone could never achieve. The moment the engineer eases the throttle, a chain reaction begins, one that unfolds along the full mile of steel and freight. The force does not hit all 70 cars at once. Instead, it travels as a wave, moving from coupler to coupler, each draft gear compressing and resisting until its spring gives up the slack. The locomotive pulls the first car, the coupler compresses, and only then does the next car start to feel the tug. It is a mechanical relay, not a single shattering jolt. A 70-car train weighing 10,000 tons takes about 30 seconds from the first nudge to the last car rolling. At the front, the lead cars creep forward almost instantly while the tail remains still, sometimes for half a minute, until the force wave finally arrives. The effect is visible from the cab. The head end accelerates gently, but the rear cars lag behind, their couplers stretching out the slack like a slow-motion ripple. By the time every car is moving, the whole train is barely at walking speed, just 1 mile per hour, but the inertia has been conquered, not by brute strength, but by a carefully managed sequence of engagements. Veteran engineers describe the sensation as a living thing. John Smith, who spent decades pulling coal out of the Powder River Basin, puts it this way: you never feel the whole train move at once. It is like dominoes. One car, then another, then another. The draft gear does the heavy lifting. All I do is keep the wheels right on the edge of slipping. This wave of force, measured and metered by every coupler, is what makes it possible for two locomotives to start a train that on paper should be immovable. The system transforms a single overwhelming challenge into a sequence of manageable steps, one car at a time. Every long freight train moves within a set of hard physical boundaries, limits that cannot be ignored or bargained with. The most unforgiving is gravity. On a 1% uphill grade, each ton of train demands an extra 20 pounds of pull. For a 10,000-ton consist, that is 200,000 pounds of force just to keep from rolling backward. Even on level track, resistance never vanishes. Aerodynamic drag grows with speed, rising as the square of velocity. By 30 miles per hour, air resistance alone adds about 27,000 pounds of pull, following a rule of thumb 0.03 pounds per ton per mile per hour squared. Curves pile on more, about 0.8 pounds per ton for every degree of bend. But the train's own hardware sets strict boundaries too. The Janney coupler, standard on North American freight, is rated for at least 300,000 pounds of draft force before risking failure. Each axle must stay under 71,500 pounds to protect the rails and bridges beneath. Exceeding these numbers is not just a bad idea, it risks catastrophic breakage or derailment. Every mile, every load, every climb must be calculated to stay inside this narrow envelope. The challenge is not just about making the train move, it is about not tearing it apart. Only by respecting these ceilings can two locomotives safely move 10,000 tons across a continent. Distributed power units are the industry's answer to the crushing forces that build up inside a mile-long freight train. By placing locomotives not just at the head but also mid-train or near the rear, operators can reduce the peak force on any single coupler by as much as 30 to 40%. This approach spreads the tractive effort, taming the whip-crack effect of slack action and enabling even longer, heavier consists to move without tearing themselves apart. But the margin for error remains razor-thin. When adhesion fails, the consequences are immediate. In one incident in Alberta, a sudden downpour dropped the coefficient of adhesion to 0.1, less than a third of what is typical on dry rail. The traction control system sensed slip and slashed power to the motors, capping each locomotive at 50,000 pounds of effort. With the grade resistance unchanged, the train stalled. As the force wave ran in, couplers compressed past their elastic limit. A handful broke, and several tank cars left the rails. NTSB investigators later noted, when adhesion drops below the minimum needed, no amount of horsepower or sand can compensate. The only option is to reduce force and hope the train holds together. Distributed power and advanced control systems buy margin, but they do not rewrite the laws of physics. Every move is a negotiation with the edge of failure. Every mile-long train crossing the continent is a test of physics, not brute force, a balance of steel, traction, and invisible limits. As global freight demands grow, these principles decide what moves and what stalls. The real engineering marvel is not size, it is knowing exactly how close to the edge you can run. For more hidden mechanics that move our world, join us next time.